And the department notify that we need to you need to fill out a form 那是什么优良老师优良教学还是什么东西的那个，对，麻烦大家帮个忙，就是那个就我不是说或者你们要公干我也可以啦，对，都没关系，对，就是可以教一下，你们公干我只要不要让我知道是公干我就好了，没有啦，开玩笑。Okay, so that's so the basic idea for the randomized quicksort. Okay, basically, as I say, it's just like randomly pick a pivot and swap that pivot to the first place. Okay, because we know the quicksort the first index is the one that will be used for pivot, right? So all the other parts remains the same for the original quicksort. So the only thing different is that, okay, it randomly swap an element to the first place as a pivot. That's it, okay? So it's a very, very simple idea, okay? So, in that case, if it's a randomized quicksort, let's try to analyze it. So that T of n to be the, the randomized variable running time for running time of randomized quicksort on an input of size n. Okay, so assuming random numbers are independent. Okay, to be honest, okay. Most of the random number generators have some this issue that random numbers are not fully independent, but that's different issue. Let's assume it's completely random. Okay, so for k equal to 0 to n minus 1, we define indicator random variable. This xk, okay, xk to be 1 if partition generates k to n minus 1 minus n minus k minus 1 split， 就是分成两个 group 的时候，它是前面第一组有 k 个，另外一组是 n 减 k 减1。为什么减1？因为减1就是个 pivot 会减掉。那当然就是前面一组已经有 k 个，所以 n 减 k 减1这是第二组的那个 size。So this is partition generate this one. Otherwise, the xk equal to 0. So expectation of xk is the probability, okay, xk equal to 1. Okay, it's 1 over n because all splits are equally likely. Okay, assuming elements are distinct. Okay, obviously. So you guys are okay with that, right? 因为所有的那种 split 都一样的几率嘛，所以说我们 xk 的那个 expectation 这个是 n 分之一这样子。Okay, then we want to do analysis on Tn, and then as I said, because Tn, it could be split into 0 n minus 1. It could be split into one element and n minus 2. Okay, up to n minus 1, 0, right? So each of them represent one possible split. Right? Okay. So of course, each of them always followed with linear cost. This is represent the cost for a partition algorithm, partition procedure. Okay, so and because we are trying to calculate the, what should I say, like the expected value of Tn. So we are, for each of these case, we need to multiply each of them with the probability, okay, that case will happen, right? 因为我们在算这个期望值嘛，所以是这个的 cost 乘上它的几率，对，这个 cost 乘上几率点点点，所以这个是不是乘上 x0啊？这个乘上 x0，加上这个乘上 x1，加点点点加上这个乘上 xk 减1，所以是这样子，全部加起来 ，OK 是这样子。Is it good？ 这个问题大家可以接受哦。OK， 一点点数学。OK，not much actually。OK， 如果你们，你们机率统计在哪一学期修的？上学也修过了嘛？对，谁教的？吴晓光老师。OK， 那理论上该会的应该会嘛？对，这个期望值，这个应该不会太夸张。好，再来 ，Let's continue. Okay, so we need to calculate the expectation of this. So we add the expectation of Tn. Okay, so expectation will be, will be applied to the whole thing. So we take expectation on both sides. Okay, and then we could, this one, we can put the expectation to like inside the parentheses, so it will become like this. Okay, so it's a linearity of expectation. We can put the e inside the summation. Okay. And then, okay, because like the xk is independent from our random choices, so we can put the e, directly to the xk times the rest of the terms. Okay, of course we will have another e here. Okay, and then this term, as we already discussed earlier, this term is actually 1 over n, right? 就是 n 分之一啦。So we put this 1 over n outside. So the rest is here. So we apply e on each term separately. Right? So far so good, right? 你们大家都还 ，You guys are still with me, right? 可以哦。那我们仔细观察一下，这个是不是 t？ 因为 k 从0到 n 减1嘛 ，because k runs from 0 to n minus 1, so we have t0, t1, t2, blah 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 to t n minus 1, right? How about here? When k is 0, what do we have? It's n minus 1, right? When k is 1, it's n minus 2, right? And when k is n minus 1, this part becomes 0, right? So you can see that this is exactly the same as this one, right? It's just the order is different, right? This one is from t0 to tn minus 1. This one is from tn minus 1 to t0. But, nevertheless, it's just the order is different. But they because we are doing the summation anyway. So the result must be the same. As for here, this is a thing, a very simple thing, because this has nothing to do with k, right? So it's just like, we have n number of this term. And then we divide it by n, right? So these two cancel out each other. So these two gets absorbed into one term. And this one is reduced to this one, right? So far so good, right? So far so good. Okay? Then it's a little bit tricky, okay? So we have here, okay? We know, like, when k is 0 and 1, these two terms, we try to absorb these two terms into like a theta n, okay, because they cannot be any larger for, than linear anyway. So we absorb the first two terms in here. So it runs down, runs from 2 to n minus 1, okay. The first two terms gets absorbed here. Okay. Then we need to prove this one is smaller or equal to a n log n, okay, for constant a greater than 0. Okay. This is what the goal. Okay. Remember, like, 大家如果记得我们前面怎么样子解那个 recurrence relation 的 how do we solve the recurrence relation? We use induction, right? We use induction. So this is the part that we introduce the induction. So this is the goal. Okay? And we need to choose a large enough so that this one dominates this thing for sufficiently small n greater or equal to 2. Okay? So we need to use the fact, this one. No. 1 over 2, okay, n squared log n minus 1 over 8 n squared, okay, is going to be greater or equal to k log n, k log k is from 2 to n minus 1. This one is an exercise I will leave for you guys to solve, okay, separately. 我们现在就是直接用这个当做事实哦，用这个当事实。但是当然你们要去确认这件事情，你们自己要去确认这件事情。这个东西是那个我会留当你们的一个练习题。记不记得我刚开始的时候，我跟你们讲说那个我会出一份作业到 E-class 上面，那这个就是作业里面的其中一题。OK， 好 ，Anyway， 那假设我们已经知道这个 ，assume we already have this， then okay, we have this, right? Because we can replace this one, okay, with this one. Okay, sorry. This is from like the substitution method. Okay, we assume like this is the case, and then plus a theta, a linear term. So, and then we substitute inductive hypothesis. We substitute with because we know this one. We have this one smaller or equal to this one, right? So we, put this thing to replace this. So we replace this part by this, and we can get A out to be here, and because we have n here, okay. So we are able to to make this thing here, a n log n minus, okay, a n divided by 4 minus theta n, okay, as long as because eventually we need to write smaller or equal to an log n. So this term has to be positive. This term in the parentheses has to be positive. So as long as we make a, we choose a large enough to guarantee an divided by 4, this term dominate the this linear term. We have this term to be positive, and then we have this inequality will, this inequality will hold. Okay. So that's like how we prove it. Along the whole process, the only thing that I didn't cover in this class is this part, which I will leave it as an exercise. This is like one inequality I want you guys to think. How to prove this fact. Okay. Okay. So you can see that this analysis, we have expected E here, right? So this is expected complexity, expected time complexity. For randomized algorithm, we usually analyze only the expected time complexity. And obviously this expected time complexity is guaranteed to be bounded by n log n. And some fact to share. First, Quicksort is a great general purpose sorting algorithm. So Quicksort is typically over twice as fast as merge sort, which is amazing, because we know merge sort is already like advanced sorting algorithm, and we also know merge sort require extra storage space, right? You need at least a linear amount of extra space to do the merge sort usually. But even with additional resource, the merge sort is still much slower than quicksort. So quicksort, that's why it gets the name quicksort. So quicksort can benefit substantially from code tuning. I mean this one I will leave you guys. I mean you can check out some literature for the code tuning of the quicksort. And the quicksort behaves well even with caching in the virtual memory. This is also very important because the modern computer, I mean, stress very heavily on caching and the virtual memory. So quicksort work well with all these features. So here's the suggestion. If you don't have so many numbers, or your numbers are almost fully sorted, then the insertion sort will be a good choice. If you have a lot of numbers and not in any particular order, or put it another way, in random order, maybe the original version of quicksort is good enough. If you have a lot of number and your numbers could be almost sorted, either ascending order or in descending order, then you should try the randomized quicksort. So this is the suggestions. And then I would like to spend some time to talk about the heap sort, because the first programming exercise will be given to you maybe next week. This is not programming exercise is not programming exam. Okay, programming exam is held at a different place, different location, and different time. But the programming exercise, I mean, you know, I'm going to give that to you as promised in the syllabus. I'll give it to you next week. So let me. I just named it lecture 4, but actually, you know, I have 2 lecture 4. I asked the TA to share this handout to you, I believe 2-3 days ago. Yeah. If you don't, if you didn't check out the E class, I mean, you may want to download it you know, now. Okay. Heap sort is also a famous advanced sorting algorithm, okay? And so here we are going to talk about, you know, priority queue, okay? The priority queue is a data structure, okay, that implement a set S of elements, okay? I mean, these elements, each of these elements is associated with a key, okay? And those keys, I mean, they support the following operation. So you are able to insert X, into S. So insert element X into set S. We call it insert SX. And the max X, S, basically, it will return the elements in the S with the largest key. Extract max X, okay, extract max S. It's going to return elements in the set S with the largest key and remove it from S. So these two are similar, but the difference is that, okay, max S, you just get that element. But extract max S, okay, not only you get that element as a return object, you also remove that element from set S. And increase key SXK, this is a function that allows you to update X key to a new value K. Okay, so this is a data structure that can allow you to do all these tasks very efficiently. Okay, priority queue. Actually, priority queue has many applications. Okay, and for example, I'm also teaching computational geometry, but well, only for the vocational students. This year, but few years ago, I also teach this class for undergraduates and the graduate students. But since Professor Yang Haozhong, joined our department, I gave this class, this course to him. So he is teaching this class regularly now, okay, for you guys. So in the computational geometry, the priority queue is used very often, okay, and not only in computational geometry, but also in, for example, computer architecture. Okay, this data structure is used very extensively. Okay, so how to implement priority queue? Okay, we usually use heap. What is a heap? Heap is an array first. heap is an array. Okay, I mean we can visualize this array as a near complete binary tree. Okay, and when you say something is a heap, it's usually associated with either max heap or min heap. Okay, let's just discuss max heap. I mean, we could. Okay, once you understand what max heap is, the min heap is just the opposite of max heap. Okay, so what is max heap? Max heap. Okay, remember it is a binary tree, right? So max heap property is the key of a node is always greater or equal than the keys of its children. Okay, so this node obviously, is applied. This property is applied to every node in this tree. So for example, this is an example of a max heap. You can see 16 is greater than 14 and 10, right? And 14 is greater than 8 and 7. Okay, 8 is greater than 2 and 4, and so on. So you can see that, okay, this property is satisfied for every locations in this tree, in this binary tree. Right? So this is the first thing you need to understand. Max heap, what max heap is. And also I want to remind you that max heap is not you don't be confused with the max heap with a binary search tree. Because we know binary search tree, you guys are in my class, so I suppose you have passed the data structure class, right? 你们已经过了资料结构的课嘛，要不然你不会在我的课，对不对 ？OK， 那你们有人回头再看不，我知道不是你啦。我说有人在看别人是那个人资料结构没有过吗？应该有啦，应该有。OK， 没过应该有党修吧？没吗？没有党修。那我要跟系上去处理一下这个，对啊，这应该资料结构跟演算法应该是有关联性的啦。OK， 像这个就很显然有关联性，就是我们在讲这个东西的时候，我说它不是 binary search tree. This is not binary search tree because for binary search tree, for a given binary search tree, the in order traversal will return you a sorted list of numbers, right? 就是如果说是 binary search tree， 你的那个 in order 的结果会是那个数字会排序好。那你可以看一下这个 in order， 那284这一看就知道不对了嘛，对不对？你再往上14、17什么的，反正你就说你看一看就知道说这不是它的 in order traversal 给你的是不是排好序的？所以 this one is obviously not a binary search tree, right? Okay, and why I said that this thing is an array? Because you can put this binary search tree elements in an array exactly in this order. 16 is index 1, 14 is index 2, 10 is index 3, and so on. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like this. Okay, so because you can see that every element has exactly the, you can see what index it is like in the array. So it is very, very convenient, okay, to consider like your max heap as an array. Not only that, there are some additional advantage. Because, if you consider this heap as an array, okay, for any given node, okay, its parent, okay, parent of I, of index I, parent of index I is at the index I divided by 2. For example, 9, its parent is here. So 9 divided by 2. I'm talking about like integer division, okay? So 9 divided by 2 is 4. Okay, 6 divided by 2 is 3, and so on. So you can see it's very easy for to find a parent once you are given the index of a node. And also, it's very easy to find the left child or right child of a node. Okay, basically, okay, the left child of a node with index I is 2i. And the right child of a node with index I is 2i plus 1. So for example, you can see index 5, its left child is 10. Well, if it will have a right child, index it will be 2 times 5 plus 1, 11. But we don't have 11 here. Okay. So you get an idea. So the heap, when you when you try to represent a heap as an array, it has several benefits. Okay, it's very easy for you to traverse. Okay, in a heap. Okay, if you are implementing the heap as an array. Okay. Once you understand that, usually to implement a tree, we know that we need to use pointers, right? If you still remember what you learned from the data structure class, if you implement a tree, you need to create a node, okay, with a data structure which contain like two pointers, one pointer pointing to the left child, one pointer pointing to the right child, and so on. That is usually how we implement the tree. But if you try to represent this complete binary tree, nearly complete binary tree, with an array, you can see that there's no pointers required. Okay, and the height of the binary heap, this binary heap, okay, is log n. Okay, where n is like in this array is 10. So this log, the base is 2. Okay, obviously. So now with this, let's try to consider, several operations for this heap. Okay, first we could like build max heap. So from an unordered array, okay, we can try to produce a max heap. How to do that? We'll talk about this. This is like once we know how to build max heap, like we are almost done with heap sort. Okay, and max heapify is like we are correct a single violation of the heap property in a subtree as its root. So that root is that single violation. In other words, that root is not, it may not be larger than its 2 children. So how do we, do something about it to correct it? Okay, that's what we call max heapify. And also remember we talk about insert, extract, max. We are also going to talk about this, and also heap sort, obviously. Okay, so let's take 10 minutes break. When we come back, we will try to talk about this. Hopefully finish this heap sort discussion today. Okay.